You think you know what World War I trenches looked like? Muddy ditches, barbed wire, men huddled in filth waiting to die. But what if I told you that beneath the Western Front, there existed an entire invisible world that would make modern engineers weep with admiration? A subterranean kingdom of innovation so sophisticated, so brilliantly engineered, that it changed warfare forever, and yet remains one of history's most overlooked marvels. This isn't the story they taught you in school. This is the story of how ordinary men became extraordinary engineers, how mathematics saved more lives than medicine, and how the greatest construction project of the 20th century happened while the world above was tearing itself apart. By the time we're done here, you'll never think about World War I the same way again. Picture this. It's November 1914. The race to the sea has ended. Two massive armies face each other across the fields of Belgium and France, and neither can move forward. Neither can retreat, and so they do something that seems utterly insane. They begin to dig. Not simple foxholes, not temporary shelters. They begin constructing what would become the most complex network of fortifications ever built by human hands, stretching from the English Channel to the Swiss border. 450 miles of frontline trenches. But here's what nobody tells you. Those frontline trenches were just the beginning. Behind every frontline trench, there were support trenches. Behind those, reserve trenches. Connecting them all, communication trenches that zigzagged back and forth to prevent enemy fire from enfilading down their length. And beneath everything, tunnels. Thousands upon thousands of miles of tunnels. If you laid out every trench, every communication line, every tunnel dug on the Western Front during World War I, you'd have enough to wrap around the Earth's equator more than 10 times. Think about that, 10 times around the planet, all dug by hand, under constant artillery fire, in conditions that would kill most modern construction workers within days. But the engineering didn't stop at just digging holes in the ground. Every trench system was a masterpiece of military engineering that had to solve problems that had never been solved before. How do you prevent tons of earth from collapsing and burying men alive? How do you drain water from a ditch when you're below the water table and pumps draw enemy fire? How do you ventilate underground spaces when you can't have chimneys giving away positions? How do you dispose of human waste for hundreds of thousands of men living in a confined space? How do you prevent disease? How do you maintain structural integrity when the ground is being constantly pounded by high explosives that would make modern demolition charges look like firecrackers? The men who solved these problems weren't career engineers. Most of them were miners, railway workers, farmers, shopkeepers. They were ordinary people thrust into extraordinary circumstances, and what they built was nothing short of miraculous. Let me take you into their world, and I promise you, it's going to blow your mind. Let's start with something fundamental that everyone gets wrong. When you picture a World War I trench, you probably imagine a straight line, right? Maybe with some minor curves. Wrong, dead wrong. The trenches weren't straight at all. They were deliberately designed in a traverse pattern, zigzagging back and forth every few yards, in a shape that looked like the crenellations of a medieval castle wall when viewed from above. Why? Because straight trenches are death traps. Imagine you're defending a straight trench and an enemy soldier makes it over your parapet. He's got a straight line of fire down the entire length of your position. Or worse, imagine an artillery shell lands in your trench. In a straight trench, the blast and shrapnel travel in a straight line, killing everyone for potentially hundreds of yards. But in a traverse trench, the blast is contained to one bay, one small section. The zigzag pattern creates blast walls. It compartmentalizes death itself. That's not luck. That's not accident. That's brilliant life-saving engineering. But the traverse pattern created its own problem. It meant men couldn't see more than 10 or 15 yards in either direction. Communication became a nightmare. You couldn't see if the enemy was in the next traverse. You couldn't coordinate attacks. You couldn't even know if your own men were alive or dead 2 traverses over. So the engineers developed something called fire bays and communication bays. Fire bays faced the enemy, packed with soldiers and weapons. Communication bays ran perpendicular, connecting the fire bays like the rungs of a ladder, allowing men and messages to move along the trench without being exposed to enemy fire. And these weren't just random ditches. Oh no. Every trench had specific dimensions that were calculated with mathematical precision. The standard British trench was 6 to 8 feet deep. Why that depth? Because it was just tall enough that a man couldn't see over the top without standing on something, which meant he was protected from direct fire, but shallow enough that he could still fire over the parapet without needing a step ladder. The width was typically 4 feet at the top, narrowing to 2 feet at the bottom. Again, not random. 4 feet was narrow enough that it couldn't be easily targeted by artillery, but wide enough for 2 men to pass each other, which was critical for moving supplies and wounded soldiers. The walls of the trench were the real engineering marvel. In most soil conditions, a 6-foot deep vertical wall will collapse. Basic physics. The earth wants to assume its angle of repose, which for most soils is about 30 to 40 degrees. So how did they keep the walls vertical? Revetments. They lined the walls with everything they could find. Wood planks, wicker hurdles, corrugated iron, sandbags, even chicken wire backed with burlap. The British preferred woven willow hurdles, which were flexible enough to absorb shell impacts without shattering, but strong enough to hold back tons of soil. The Germans, in typical German fashion, built with more permanence. They used concrete and steel wherever possible, treating trenches not as temporary positions but as fortresses. Let me tell you about the German engineering because it was on another level entirely. While the British and French were building trenches they hoped to leave behind when they advanced, the Germans were building to stay. They went deep, really deep. Some German dugouts went down 40 feet or more, effectively becoming underground bunkers that could withstand even the heaviest bombardment. They had multiple levels, reinforced with concrete pillars and steel beams, electric lights powered by generators, ventilation systems, beds, tables, even wallpaper in some cases. These weren't trenches. These were underground fortresses. The Germans understood something the Allies didn't grasp until much later in the war. Depth equals survival. The deeper you go, the more protection you have from artillery. But going deep creates its own nightmares. How do you get air down there? How do you get water out? How do you prevent carbon monoxide poisoning from lamps and stoves? How do you keep hundreds of men from going insane in the dark? The ventilation systems they developed were ingenious. They couldn't use simple chimneys because smoke and heat signatures would draw artillery fire like moths to a flame. So they developed passive ventilation systems using the principle of convection. They dig multiple shafts at different levels. Warm air rises, so the upper shafts would become exhaust vents, while the lower shafts drew in fresh air. They disguised the openings as shell craters or debris. Some German engineers even developed elaborate baffled systems that dispersed the exhaust over a wide area, making it nearly invisible. But the biggest engineering challenge wasn't the trenches themselves. It was water. Water was the true enemy on the Western Front, and it was an enemy that never slept, never retreated, never signed truces. The moment you dig a hole in Flanders, it fills with water. The water table in parts of Belgium is less than 3 feet below the surface. Imagine trying to dig a 6-foot deep trench when you hit water at 3 feet. What do? The answer is drainage. And not just simple drainage. We're talking about complex hydrological engineering that would impress modern civil engineers. The British developed elaborate sump systems where water would naturally collect at the lowest points, then be pumped out using hand pumps or, later in the war, mechanical pumps. But pumps were a problem. They made noise. They drew attention. A pumping station could be located by sound detection equipment and targeted with artillery. So the engineers developed quieter pumps, camouflaged pumps, pumps that ran only at night or during artillery barrages when the noise would be masked. The French, dealing with different soil conditions in their sectors, developed a different solution. They built raised wooden floors, called duckboards, that kept men above the water level. These weren't just planks thrown across mud. They were engineered systems with proper drainage underneath, angled to direct water flow to collection points. Walk along a French trench and you'd be walking on a wooden boardwalk 6 inches to a foot above the actual trench floor, with water flowing beneath your feet. In the worst areas, particularly around Passchendaele, the ground was so saturated that traditional trenches were impossible. The solution? Breastworks. Instead of digging down, they built up. They'd fill sandbags and stack them to create walls above ground level, then build a firing step behind them. It was the same principle as a trench, but inverted. Of course, breastworks had their own problems. They were more visible, which made them easier targets. They required constant maintenance as sandbags deteriorated. And they offered less protection, because you couldn't go as high as you could go deep without creating an obvious target. But here's something that will absolutely blow your mind. The drainage systems in the trenches weren't just about keeping feet dry. They were about preventing disease. The engineers understood, even if they didn't fully grasp germ theory, that standing water meant disease. Trench foot, which could rot flesh from bone and required amputation, was caused by prolonged exposure to cold, wet conditions. Cholera, typhoid, dysentery, all waterborne diseases that could decimate an army faster than any enemy bullet. So drainage wasn't just an engineering problem, it was a medical problem, a tactical problem, a strategic problem. The British Army eventually assigned entire companies of engineers just to maintain drainage. They'd work through the night, clearing sumps, repairing pumps, digging new drainage channels. It was backbreaking, dangerous work that never ended. A single artillery barrage could destroy days of drainage work in seconds, collapsing carefully engineered channels, filling sumps with debris, breaking pump systems, and then they'd start over. Now let's talk about something even more remarkable. The trench systems weren't static. They were constantly evolving, constantly being improved, constantly being adapted. Every night, working parties would go out to strengthen parapets, deepen dugouts, extend communication trenches, repair damage from the day's shelling. The Western Front wasn't a construction project that was finished and then maintained. It was a construction project that never stopped. A living, breathing, constantly changing structure. And the material logistics of this constant construction were staggering. The British Army calculated that a single division, about 15,000 men, occupying a mile of front line, required 30 tons of timber per week just for maintenance. Not for new construction, just to maintain existing structures. 30 tons every week. For 4 years. Where does that timber come from? How do you transport it to the front lines? How do you distribute it to where it's needed? The answer is one of the most underappreciated aspects of World War I engineering. The light railways. Behind the front lines, the Allies built thousands of miles of narrow gauge railway track, typically 60 centimeter gauge, about 2 feet wide. These railways could snake through areas where standard gauge trains couldn't go, could navigate the shell-cratered landscape. could bring supplies within a few hundred yards of the front lines. They were the circulatory system of the trench networks, the arteries that kept everything alive. The engineering of these railways was fascinating. The track had to be portable, able to be laid and torn up quickly as the front line shifted. The engines had to be small and light enough not to sink in soft ground, but powerful enough to haul significant loads. The cars had to be versatile, capable of carrying everything from timber to ammunition to wounded soldiers. And the whole system had to operate under constant artillery fire, with crews ready to repair broken track, replace destroyed bridges, and clear wreckage, sometimes under enemy observation. But we haven't even gotten to the most incredible part yet: the underground war, beneath the trenches, beneath the mud and water and death. There was another world entirely. A world of tunnels and mines and underground chambers where men fought in complete darkness, where sound was your only warning of death, where mathematical precision was the difference between victory and annihilation. Mining warfare in World War I was unlike anything that had come before. The objective was simple but terrifying: dig a tunnel under enemy trenches, pack the end with explosives, blow it up, and advance into the crater before the enemy can recover. But the execution was anything but simple. These weren't shallow tunnels. We're talking about tunnels that went down 60, 80, even 100 feet, then extended horizontally for hundreds of yards under no man's land, under enemy trenches, sometimes even under enemy support lines. The engineering challenges were immense. First, you had to deal with geology. The Western Front ran through incredibly varied terrain. In some places, you had solid chalk that was easy to tunnel through and held its shape well. In others, you had wet clay that was stable but exhausting to dig. In the worst areas, you had running sand that would collapse without warning. Or worse, liquid mud that would flow like water. The tunnelers had to understand geology like miners, but they also had to be silent like thieves, because the enemy was doing exactly the same thing. And if two opposing tunnels met underground, the result was brutal close-quarters combat in absolute darkness with picks, shovels, and knives. The British tunnelling companies were manned by miners recruited from coalfields across Britain and the Commonwealth. These were men who'd spent their lives underground, who understood rock and earth, who could read the ground by touch and sound. They developed techniques that were absolute genius. To detect enemy tunneling, they used geophones, essentially stethoscopes for the ground. A geophone could detect the sound of digging from dozens of yards away. The listener, usually the most experienced miner in the company, would mark the location and direction of enemy digging, allowing British miners to intercept the tunnel or to avoid being intercepted themselves. The mathematics of mining warfare was complex. You had to calculate the exact amount of explosives needed based on the depth of the mine and the type of soil. Too little, and you'd blow a small crater that the enemy could defend. Too much, and you'd create a crater so large that your own troops couldn't cross it. The formula, developed through trial and error and mathematical modeling, related the charge weight to the cube root of the depth. A mine at 60 feet deep required exponentially more explosives than one at 30 feet to achieve the same effect. Get the math wrong and men died, either because the attack failed or because they were caught in their own crater. The largest mines ever detonated in warfare up to that point were the Messines Ridge mines in June 1917. British tunnelers spent over a year digging 21 separate mine shafts under German positions on Messines Ridge. They planted a total of nearly £1 million of explosives. When they were detonated simultaneously, the explosion was heard in London, over 130 miles away. It was the loudest human-made sound in history up to that point. The blast killed an estimated 10,000 German soldiers instantly and created craters so large that some are still visible today, a century later. But here's what's truly remarkable about the mining operations. The engineering sophistication. These weren't simple tunnels. They were complex systems with air shafts, electric lighting, hand-pumped ventilation systems, drainage sumps, and structural supports. The main tunnels were large enough for men to walk upright. Side galleries branched off for storing explosives, for listening posts, for rescue operations. The German miners, true to form, went even further, creating underground barracks, first aid stations, even entire company headquarters beneath the surface. The timbering of these tunnels was an art form. In stable chalk, they could use simple props, wooden beams set at intervals to support the roof. In less stable ground, they used close timbering, where every inch of the tunnel was lined with wood. The timbers had to be precisely cut, precisely angled, interlocking to distribute the load. Too loose and the tunnel would collapse. Too tight and the wood couldn't flex with ground movement, leading to catastrophic failure. The tunnelers could tell by sound whether their timbering was adequate. A solid tunnel has a certain acoustic quality. A failing tunnel sounds different, and experienced miners could hear the warning signs hours or even days before collapse. And let's talk about the human element of this underground warfare, because it was psychologically devastating. Imagine spending 12-hour shifts in absolute darkness, sometimes in tunnels so narrow you have to crawl, where the air is so bad that candles won't stay lit, where every sound might be an enemy miner on the other side of a thin wall of clay, where at any moment the enemy might blow a camouflage, a small defensive mine designed to collapse your tunnel and bury you alive. The stress was unimaginable. Tunnelers had some of the highest rates of psychological breakdown in the entire war. They called it shell shock above ground, but underground it was something else entirely. The darkness, the closeness, the constant awareness that thousands of tons of earth could collapse on you at any second. It broke men in ways that surface combat didn't. Now, let's shift our focus to something equally important, but often overlooked. The logistics and infrastructure that made the trench systems viable. 100,000 men living in a relatively small area require food, water, ammunition, medical supplies, mail, replacements, and 1,000 other necessities. How do you deliver all that when every supply route is under observation and fire? The answer was a carefully engineered network of communication trenches, roads, and pathways that stretched from the front lines all the way back to supply depots miles behind the lines. The communication trenches alone were engineering marvels. They had to be deep enough to provide protection from observation, which meant 6 feet or more. They had to be wide enough for supplies to pass through, which meant 4 to 5 feet. And they had to be routed to avoid natural killing zones where enemy artillery was pre-registered. But here's the clever part. The communication trenches were deliberately routed in zigzag patterns, just like the frontline trenches. But the angles were calculated to maximize protection from enfilade fire while minimizing the walking distance. It was an optimization problem that would challenge modern computer algorithms. You're trying to connect point A to point B, but you can't go in a straight line. You have to zigzag, but every zigzag adds distance, and distance means time, and time means men are exposed longer, and exposure means casualties. So where do you put the angles? How sharp do you make them? How many do you need? The British Army had entire staff sections devoted to calculating optimal trench routes. They'd use aerial photography to map enemy positions, identify dead ground where trenches could run with less risk, and plot courses that balanced protection with efficiency. It was military engineering meets operations research, and it saved countless lives. The roads behind the lines were another engineering marvel. You can't drive trucks or heavy wagons through shell-cratered mud. So the engineers had to build roads. In some cases, they could improve existing roads by adding drainage, widening them, reinforcing them. But in many areas, particularly around Ypres and the Somme, they had to build roads from scratch, sometimes on top of existing roads that had been shelled into oblivion. The road construction technique they developed was called plank road building. They'd lay down a foundation of brush and rubble to provide a stable base above the mud, then lay wooden planks across to create a solid surface. These plank roads could support heavy traffic and were relatively quick to build, but they required constant maintenance as planks broke, shifted, or were destroyed by shellfire. During major operations, engineer companies would be assigned solely to maintain specific sections of road, working around the clock to keep supplies moving, and water supply. We talked about getting water out of the trenches, but what about getting clean drinking water to troops? A man needs about a gallon of water per day just for drinking and basic hygiene. 100,000 men need 100,000 gallons per day. Where does it come from? The local water was contaminated with human waste, dead bodies, chemicals from explosives, and every disease you can imagine. Drinking local water was suicide. The solution was engineered water supply systems. The British Army deployed water purification units that used sand filtration and chlorination to produce safe drinking water. They built storage tanks behind the lines and laid pipes to forward distribution points. In some areas, they even built aqueduct systems using salvaged pipes and creative engineering to bring water from sources miles away. The scale of these operations was immense. By 1917, the British Army on the Western Front was operating water purification plants with a combined capacity of over 3 million gallons per day. Waste disposal was another nightmare that required engineering solutions. You can't have 100,000 men living in a confined area without dealing with human waste. Latrines had to be dug, maintained, and eventually filled in and moved when they became full or when positions shifted. But it wasn't just a matter of digging a hole. Latrines had to be positioned to prevent contamination of water supplies. They had to be accessible but not so close to living areas that they created unbearable conditions. They had to be covered and ventilated to control flies, which carried disease. And they had to be designed so they could be quickly filled in if positions were overrun. The British Army developed standardized latrine designs with proper drainage, seats, covers, and even rudimentary ventilation. The French went further in some areas, installing actual flush toilets connected to septic systems in rear areas. The Germans, obsessed with cleanliness and order, had the most elaborate systems, with some positions featuring tiled latrines with running water. It sounds absurd to talk about bathroom engineering in the middle of a war, but disease killed more soldiers in every war prior to World War I than combat did. The engineering that went into sanitation probably saved more lives than any weapon. Let me tell you about one of the most ingenious pieces of engineering that emerged from the trenches: the Stokes mortar. Now, you might think a mortar isn't engineering, it's a weapon. But the Stokes mortar represented a revolution in both weapon design and trench engineering. Before the Stokes mortar, if you wanted to attack enemy trenches, you needed artillery, which meant guns positioned miles behind the lines, forward observers, complex calculations, and usually terrible accuracy. Or you needed to go over the top with rifles and hope for the best. The Stokes mortar changed everything. It was a simple tube that could be carried and set up by 2 men. You dropped a bomb down the tube, it hit a firing pin at the bottom, and it launched in a high arc that could drop almost straight down into enemy trenches. The range was short, only a few hundred yards, but the accuracy was incredible. And here's the engineering brilliance. The bomb was designed to be fin stabilized, which meant it always fell nose down, always detonated on impact, and could be mass-produced with simple manufacturing. But the real genius was in how it integrated with trench systems. Mortar pits could be dug into the support trenches with calculated angles to fire over the front lines without exposing the crew. The pits had to be engineered to absorb recoil, to provide blast protection, to allow quick escape if the position was targeted. The British Army calculated optimal pit designs based on soil type, proximity to front lines, and rate of fire. It was engineering in service of tactics, in service of strategy. Speaking of weapons integration, the machine gun changed trench engineering entirely. Early trenches didn't account for machine guns because early military thinking didn't grasp their significance. But by 1915, everyone understood. Machine guns were the queens of the battlefield. A single machine gun with good fields of fire could hold off a battalion, so trenches had to be designed around machine gun positions. Machine gun nests became miniature fortresses within the trench system. They needed overhead protection from artillery, which meant reinforced roofs. They needed clear fields of fire, which meant precisely calculated angles and heights. They needed to be positioned to provide interlocking fire where one gun could cover the approach to another. And they needed to be concealed, which meant camouflage, false positions, and carefully engineered firing slits. The Germans were masters at this. They'd build concrete machine gun pillboxes with walls 2 feet thick, designed to withstand direct hits from field artillery. The firing slits were calculated to give maximum field of fire while exposing minimum surface area. Some pillboxes had multiple firing ports, so the gun could be quickly moved if one position was compromised. They'd camouflage them to look like rubble or shell damage. Allied soldiers would advance thinking they were attacking an abandoned position, only to have machine guns open up from what looked like piles of broken concrete. The British eventually developed similar systems, but they also came up with something else. Mobile machine gun posts. These were engineered positions that could be quickly set up or torn down, allowing machine guns to be repositioned as tactics changed. They'd use standardized components, pre-built shields and supports that could be carried forward and assembled like deadly Lego sets. It was modular engineering applied to trench warfare. Now we need to talk about perhaps the most sophisticated engineering challenge of all: observation and targeting. In trench warfare, if you can see the enemy, you can kill them. But if they can see you, you die. So the entire war became a battle of who could see without being seen, who could observe and target without being observed and targeted in return. The solution was observation posts, and these were engineering marvels in their own right. The simplest were just periscopes, mirrors mounted on sticks, so you could look over the parapet without exposing your head. But periscopes had limited range and field of view. For long-range observation, you needed height, but anything tall is a target. So how do you build an observation post that's tall enough to see but doesn't scream artillery target here? The answer was camouflage and deception. The British built observation posts disguised as dead trees. They'd find a blasted tree stump in no man's land, usually one with a clear view of enemy positions. At night, they'd remove the actual stump and replace it with a hollow steel replica containing a ladder and observation platform. The replica was painted and textured to match the original stump exactly. From even a short distance, it was indistinguishable from the real thing. Engineers would spend weeks planning a single tree installation, measuring, photographing, building the replica in workshops behind the lines, then executing the switch in a single night. The observer would climb up inside before dawn and spend the day gathering intelligence, then evacuate after dark. It was incredibly dangerous, claustrophobic, and vital. The engineering that went into these fake trees was remarkable. They had to be structurally sound enough to support a man and equipment. They had to be waterproof. They had to have ventilation that didn't create visible air currents. They had to be balanced, so they didn't lean differently than the original tree. And they had to be installed perfectly vertical because even a slight tilt would give away the deception to aerial observation. But the ultimate observation posts were the purpose-built towers and platforms in rear areas. These were engineered structures that could rise 30 or 40 feet, providing observation posts for artillery spotters. They had to be stable enough to support men and optical equipment. They had to have anti-vibration mounting for telescopes because even breathing would blur the view at high magnification. And they had to be camouflaged or positioned to minimize their value as targets. Some were built to look like buildings. Others were surrounded by trees or hills that concealed their true height. The engineering that went into these structures would be impressive in peacetime construction, let alone under wartime conditions. And let's talk about aerial observation, because that's where engineering and aviation intersect in fascinating ways. Aerial photography transformed warfare, allowing commanders to see the enemy trench systems from above, to map them, to identify weaknesses. But aerial photography in 1915 was crude. You'd fly over, snap pictures with a handheld camera, hope they came out, hope you could interpret them, hope the information wasn't already outdated. By 1918, it had become an engineering discipline. Photo reconnaissance aircraft had specially mounted cameras with calculated focal lengths to produce images at specific scales. The film and development process was standardized to produce consistent results. Interpretation became a science, with trained photo interpreters using stereoscopic viewers to see enemy trenches in 3 dimensions, to measure the depth of trenches and dugouts, to identify new construction or changes from previous photos. And all of this information was fed into mapping systems that produced detailed trench maps distributed to units before attacks. The engineering of the photography itself was impressive. The cameras had to be stabilized to prevent blur from aircraft vibration. They had to have shutters fast enough to freeze motion. They had to have enough film capacity to capture long strips of terrain in overlapping images that could be stitched together. And all of this had to work at altitude, in cold, in planes that were shaking and bouncing through turbulence and sometimes enemy fire. The fact that they made it work at all is a testament to human ingenuity. Now let's dive into something that literally kept soldiers alive but almost never gets mentioned: the communication systems. In trench warfare, communication was everything. If you couldn't tell headquarters that you were being attacked, you'd get no reinforcements. If you couldn't coordinate artillery support, your attacks would fail. If you couldn't warn adjacent units of enemy movements, gaps would open in your line. But how do you communicate when you're in a ditch, under fire, with no line of sight to anyone more than 20 yards away? The telephone revolutionized trench warfare, but making it work required incredible engineering. You couldn't just string telephone wire along the ground. Artillery would cut it in seconds. You couldn't string it overhead because it would be visible and easily targeted. So the solution was to bury it deep. The British developed specialized cable laying equipment that could plow trenches 6 feet deep and lay telephone cable in a single pass. They laid thousands of miles of buried cable connecting every command post, every battery, every headquarters across the Western Front. But buried cable created its own problems. How do you find a break in 6 feet of buried wire? The answer was electrical engineering. They developed cable testing equipment that could measure resistance and capacitance to locate breaks to within a few yards. Then specialized repair teams would dig down, splice the cable, and rebury it, often under fire. During major battles, cable breaks were so frequent that some repair teams were stationed along critical routes, waiting for breaks they knew would come. The Germans went even further. They developed armored cables with steel wrapping that could survive near misses from artillery. They built cable distribution centers in concrete bunkers that could take direct hits and keep functioning. They treated their communication network like critical infrastructure, which it absolutely was. A functioning telephone network could mean the difference between a successful defense and total collapse. But telephones had a fatal flaw. They could be tapped, run a wire to enemy lines, clip onto their cable, and you could listen to their conversations. Both sides did this constantly, so sensitive communications had to be coded, which meant code books, training, and time delays that could be fatal in fast-moving situations. The alternative was runners, human messengers who would physically carry messages from one position to another. These men had some of the most dangerous jobs in the entire war. They had to navigate through artillery barrages, across open ground, through communication trenches that might be blocked or collapsed, all while carrying messages that could determine the fate of thousands of men. The engineering response was to create protected runner routes, covered communication trenches with overhead protection, slit trenches too narrow for effective artillery targeting, route planning that used shell craters and dead ground. Some positions even had tunnel systems specifically for runners, underground routes that connected command posts to frontline positions. It was infrastructure engineering applied to human movement under fire. And then there were the signal systems. Flags, flares, lamps, anything that could convey information without wire. But every signal system had to be engineered to be visible to friendly forces, but not enemy forces, or at least not obviously interpretable by the enemy. Flares came in different colors, different patterns, different burn times, each meaning something specific. Green flare meant attack imminent. Red meant artillery needed. White meant all clear. But the engineering of the flares themselves was complex. They had to burn bright enough to be seen in daylight, specific enough in color to not be confused, weatherproof, safe enough to store and handle under combat conditions. The pyrotechnic engineering that went into military signal flares was surprisingly sophisticated. Let me tell you about something that sounds mundane but was actually brilliant. Engineering. Duckboards. Remember I mentioned them earlier. These wooden walkways that kept men above the water. They weren't just random planks. They were precisely engineered components. Standard British duckboards were 9 feet long, 2 feet wide, made from wooden slats spaced ½ an inch apart to allow water and mud to drain through. The slats were nailed to crossbeams positioned to distribute weight. The whole assembly could be carried by 2 men and connected to other duckboards with simple overlaps. But here's the genius. The spacing, width, and length weren't arbitrary. They were calculated based on the stride of a walking man, the weight distribution of a man carrying equipment, the typical span between trench walls, and the standard dimensions of supply sleds that would be dragged over them. They were modular components in a massive construction system. Millions of duckboards were manufactured, shipped to France, and assembled into miles of walkways that made the trenches marginally livable. And they had to be constantly maintained. A broken slat could break an ankle. A missing duckboard could mean a man falls into freezing water with 60 pounds of equipment and drowns in 3 feet of liquid mud. Engineer units assigned to trench maintenance spent enormous amounts of time just repairing and replacing duckboards. It was unglamorous work that saved more lives than most people will ever realize. Now, we're going to talk about something genuinely terrifying that required some of the most advanced engineering of the entire war: gas warfare. When the Germans released chlorine gas at Ypres in April 1915, they opened a new chapter in military horror, but they also created an engineering arms race that would produce some of the most sophisticated protective equipment and delivery systems ever developed. The first gas masks were crude, cloth soaked in urine or chemical solutions held over the face. They barely worked. Within months, engineers had developed proper respirators with charcoal filters, rubber seals, glass eyepieces. But each improvement in gas masks drove improvements in gas weapons. The Germans developed phosgene, which was more lethal and harder to filter. The British responded with better filter materials. Then came mustard gas, which didn't need to be inhaled. It burned skin on contact, seeped through clothing, could persist for days or weeks. The engineering of gas masks became incredibly sophisticated. The filters had to remove specific chemicals from air while allowing enough airflow for a man to breathe, even while exerting himself. The seals had to be perfect because even a tiny leak could be fatal. The eyepieces had to be clear, not fog up, resist chemical attack, and the whole assembly had to be comfortable enough that men would actually wear them, durable enough to survive combat conditions, cheap enough to produce in millions. The British smallbox respirator, introduced in 1916, was an engineering marvel. It used activated charcoal impregnated with specific chemicals to filter out chlorine, phosgene, and other gases. The filter box hung on the chest, connected to a rubber face piece with a flexible tube. The face piece had an oral nasal cup that forced air through the filter before it reached the lungs. The eyepieces were made of triplex glass that resisted shattering and chemical fogging, and the whole system could be donned in under 6 seconds, which was critical because gas could spread across a position in less than a minute. But the engineering didn't stop at defense. Gas delivery systems were complex weapons that required precise engineering to be effective. Early gas attacks relied on releasing compressed gas from cylinders and hoping the wind would carry it toward enemy lines. This was crude and dangerous. If the wind shifted, your own gas could blow back and kill your own troops. So engineers developed gas shells that could be fired from artillery, delivering gas precisely where you wanted it. Gas shells had to solve multiple engineering problems. The shell had to survive the launch acceleration without the gas container rupturing. It had to burst at the right altitude to disperse the gas effectively. The chemical payload had to be stable enough to store, but volatile enough to disperse rapidly on burst. Different gases required different shell designs. Phosgene shells had thin walls to maximize chemical payload. Mustard gas shells needed thicker walls because mustard gas was corrosive and would eat through weak containers. The Germans developed specialized gas projectors called Gaswurfminen that could throw canisters of gas hundreds of yards. These were essentially mortars optimized for chemical delivery. The canisters would tumble through the air and burst on impact, saturating an area with gas. The engineering required to make these reliable was impressive. The projectiles had to be aerodynamically stable despite their awkward shape. The burst mechanism had to be reliable, and the launchers had to be safe for the crews operating them. Now let's shift to something that sounds simple but was actually incredibly complex. Barbed wire. Everyone knows about barbed wire in World War I, but few people understand the engineering that went into its deployment. This wasn't farm fence wire strung between posts. This was military obstacle engineering on an industrial scale. The standard deployment was belts of wire up to 30 yards deep, not strung in neat lines, but woven in random patterns at varying heights to trip, entangle, and channel attackers into killing zones. The wire was held up by iron stakes driven into the ground, and even those stakes were engineered components. They had to be silent to drive in, which meant spiral stakes that screwed into the ground rather than being hammered. They had to be strong enough to hold wire under tension. They had to be the right height, typically 3 to 4 feet, to be most effective against infantry. The wire itself came in different types: simple barbed wire with barbs every few inches, concertina wire that could be rapidly deployed by unrolling preformed coils, knife rest obstacles, wooden frames wrapped in wire that could be quickly positioned or moved. Each type had specific tactical applications and required specific engineering. The Germans developed a particularly nasty variant with larger, sharper barbs that were more difficult to cut. The French developed expanded metal obstacles that combined wire with steel mesh. But here's what's fascinating from an engineering perspective. Deploying wire obstacles required mathematical planning. You couldn't just randomly string wire and hope for the best. Engineers had to calculate fields of fire, ensuring that machine guns and rifles could cover the entire wire belt with interlocking fire. They had to create gaps that could be opened for friendly patrols or attacks, then closed again. They had to consider how the wire would channel attackers and ensure those channels led into the deadliest fire zones. And the wire had to be maintained. Artillery would blast gaps in it. Patrols would cut paths through it. Rain, wind, and simple deterioration would weaken it. Every night, wiring parties would go out into no man's land to repair and strengthen the wire. This was incredibly dangerous work. They had to work silently to avoid drawing fire, but they also had to work effectively, which meant carrying heavy coils of wire, stakes, tools. If an enemy flare went up, they'd freeze in the open, exposed. Many men died hanging wire in the dark. The engineering extended to wire cutting as well. How do you get through 30 yards of barbed wire when attacking? Artillery could blast gaps, but artillery was imprecise and often just tangled the wire worse. Wire cutters could work, but cutting through that much wire under fire was suicidal. The British developed Bangalore torpedoes, explosives in metal tubes that could be pushed under wire and detonated to blast a path. The engineering of these weapons was tricky. The explosive had to be powerful enough to destroy wire and stakes, but shaped to direct the blast upward and outward. The tubes had to be rigid enough to push through obstacles, but light enough for infantry to carry. Later in the war, tanks rendered much of the wire obstacle engineering obsolete. But even then, the Germans responded with engineering solutions. Anti-tank obstacles, concrete blocks, deep ditches, all designed to stop or channel tanks. It was an endless engineering arms race. Let's talk about one of the most overlooked aspects of trench engineering: camouflage. Modern military camouflage began in World War I, and it was an engineering discipline that combined optics, psychology, materials science, and tactical planning. The problem was simple to state, but devilishly hard to solve. How do you hide an enormous infrastructure of trenches, roads, gun positions, and supply dumps from aerial observation? The French were the pioneers. They established dedicated camouflage units staffed by artists and engineers working together. The artists understood color, pattern, and visual perception. The engineers understood materials, structure, and practical deployment. Together, they developed camouflage systems that were remarkably effective. The basic principle was disruption. You couldn't make a trench invisible, but you could break up its visual signature so it didn't read as a trench from the air. They'd use painted canvas, netting with vegetation attached, actual transplanted vegetation, anything to disrupt the straight lines and geometric patterns that screamed man-made structure to aerial observers. Gun positions would be covered with painted screens that from above looked like ordinary fields or roads. Supply dumps would be hidden under netting that mimicked tree cover. But the engineering was in the details. Camouflage nets had to be supported on frameworks that wouldn't collapse under rain or wind. The painted patterns had to account for shadows and perspective from typical observation altitudes. The materials had to be durable enough to last through weather, but light enough to be portable, and everything had to be maintainable, because camouflage that wasn't maintained was worse than no camouflage. A torn net or faded paint would actually highlight what you were trying to hide. The Germans took camouflage engineering to another level. They built entire dummy positions, fake trenches and gun emplacements designed to draw enemy fire away from real positions. These weren't crude mock-ups. They were engineered to look real from the air, complete with dummy guns made from logs, fake supply dumps, even staged activity to suggest the positions were occupied. The British and French would waste ammunition bombarding empty fields, while real German positions remained untouched. And then there was deception engineering, fake roads that led nowhere, fake railway lines, even fake hospitals marked with red crosses to make the enemy think a sector was a rear area when it was actually close to the front. The engineering required to make these deceptions convincing was substantial. A fake road had to have the right width, the right texture when photographed from above, the right pattern of ruts and tracks. A fake railway had to have properly spaced ties, the right gauge, even fake stations or sidings. Now we need to discuss something that will absolutely astound you: the underground cities. I mentioned earlier that the Germans built deep dugouts, but I didn't fully convey the scale. In some sectors, particularly around Arras, both sides went far beyond simple dugouts. They created vast underground complexes that were essentially subterranean cities. The Arras tunnels are the most famous example. Beneath the town of Arras, British engineers expanded existing medieval quarries and cellars into a network of tunnels that could shelter 24,000 men. 24,000. That's an entire division, hidden underground, immune to artillery, capable of massing for an attack without the enemy having any idea they were there. The engineering required to make this work was phenomenal. First, they had to map the existing tunnel systems, some of which dated back to medieval times. Then they had to determine which tunnels were stable, which needed reinforcement, and where new tunnels needed to be dug. They had to install ventilation systems capable of providing fresh air to thousands of men. They had to install electric lighting throughout the complex, which meant generators, wiring, and maintenance. They had to provide water, which meant pumps and pipes. They had to handle sanitation for thousands of men, which meant elaborate latrine systems and drainage. And they had to do all of this while maintaining operational security. The Germans knew the British were up to something, but they didn't grasp the scale until it was too late. The tunnel system had multiple exits into no man's land, carefully engineered so that thousands of men could emerge quickly when the attack began. The exits had to be concealed, reinforced against collapse, and positioned to provide cover as men emerged. The Germans built similar systems. The Hindenburg Line, constructed in 1916 and 1917, wasn't just trenches. It was a fortified zone with dugouts that went down 30 or 40 feet, connected by tunnels with multiple levels, electric power, concrete reinforcement, and amenities that made them livable for extended periods. Some German dugouts had multiple rooms, sleeping quarters separated from living areas, officer quarters separate from enlisted men, even recreational spaces. They had furniture, stoves, water systems, everything needed for men to live underground for weeks or months. The engineering challenge of these deep systems was ventilation. You can't have thousands of men underground without massive amounts of fresh air. The Germans used forced air systems, essentially large bellows or mechanical fans that pushed air through distribution pipes. The British used convection systems where possible, but also deployed portable generators and fans. The air distribution pipes themselves had to be engineered to provide even airflow, to prevent dead zones where carbon dioxide would accumulate, to filter out gas if chemical weapons were used above ground, and lighting. Before electric light, underground spaces were illuminated by candles or oil lamps, which consumed oxygen and produced carbon monoxide. Electric lighting was safer, but required engineering infrastructure. Generators had to be installed, usually in chambers isolated from living spaces to reduce noise and fumes. Wiring had to be run through damp tunnels, properly insulated and protected from damage. Light fixtures had to be durable and safe. The Germans even developed explosion-proof fixtures for use in ammunition storage areas. The logistics of these underground cities were staggering. Food for 20,000 men, water for drinking, cooking, and basic hygiene, medical facilities for treating sick and wounded, storage for ammunition and equipment. All of this had to be brought in through limited access points, distributed through the tunnel system, and managed efficiently. The British developed underground supply depots, essentially warehouses in converted tunnels, with inventory systems and distribution schedules. Let me tell you about the medical infrastructure because it's another engineering marvel that saved countless lives. The traditional image of World War I medicine is of crude field hospitals in tents, but the reality was far more sophisticated. The British developed a system of casualty evacuation and treatment that was, for its time, remarkably advanced, and it was all enabled by engineering. The system started at the front line with regimental aid posts, usually in reinforced dugouts just behind the front trenches. These had to be positioned close enough for quick access, but far enough back to avoid constant shelling. They needed multiple entrances for bringing in wounded. They needed lighting, ventilation, and enough space for medical personnel to work. The engineering was in creating spaces that were functional medical facilities in holes in the ground. From the aid posts, wounded would be evacuated to advanced dressing stations, typically a mile or two behind the lines. These were larger facilities, often in existing buildings or specially constructed huts, with operating rooms for emergency surgery. The buildings had to be reinforced against shelling, clearly marked with red crosses, and positioned near transport links, usually the narrow gauge railways. The railways were the key to the whole system. Wounded men would be loaded onto specially designed ambulance cars that were essentially mobile hospital wards. These cars had racks for stretchers, suspension systems to minimize jolting, lighting, heating, ventilation, and space for medical staff to work during transport. The engineering that went into these cars was impressive. They had to ride smoothly on rough track, maintain stable temperatures in all weather, and be easy to load and unload even under difficult conditions. From the railhead, wounded would go to casualty clearing stations, large hospital facilities several miles behind the front. These were essentially full surgical hospitals with operating theatres, recovery wards, X-ray equipment, laboratories, everything needed for modern medical care. The engineering extended to the hospital design itself. Operating theaters needed good lighting, which meant electrical systems or skylights positioned to maximize natural light. They needed sterilizable surfaces, which meant tiled walls and floors. They needed water and drainage, heating and ventilation, all the infrastructure of a civilian hospital, but built in a war zone. The X-ray equipment alone was an engineering challenge. Early X-ray machines were bulky, required electrical power, and produced images on glass plates that had to be developed in dark rooms. Getting these systems to work in field conditions, making them mobile enough to deploy close to the front lines, training operators to use them effectively. This all required engineering solutions. By 1918, the British had mobile X-ray units mounted in vehicles that could be driven to casualty clearing stations and set up within hours. The engineering even extended to prosthetics and rehabilitation. The number of amputees from the war was staggering, and helping these men return to productive lives required engineered solutions. Artificial limbs had to be functional, comfortable, durable, and affordable to produce in large numbers. Rehabilitation hospitals needed equipment for physical therapy, training facilities for teaching new skills, accommodations for long-term care. The engineering that went into supporting wounded soldiers after they left the battlefield was as important as the engineering that saved them on it. Now let's talk about something that rarely gets discussed but was absolutely critical: pioneering equipment and tools. The men building the trenches needed tools, and not just any tools. They needed tools specifically engineered for trench warfare conditions. Standard civilian tools often weren't adequate. Take the humble shovel. In civilian life, a shovel is a shovel. In trench warfare, the type of shovel could mean the difference between efficient work and exhausted men. The British Army tested dozens of shovel designs before settling on the standard issue tools. They had to be strong enough to cut through roots and clay, light enough for men to carry along with all their other equipment, durable enough to last through hard use, and shaped correctly for efficient digging in confined spaces. The trenching tool, a short-handled shovel, was specifically engineered for work in trenches where a long-handled shovel couldn't be effectively swung. The shape of the blade, the angle of the handle, the material composition, all were calculated for maximum efficiency. They even conducted time and motion studies to determine the optimal technique for digging in various soil conditions. Wire cutters had to be powerful enough to cut through heavy gauge wire, precise enough for close work, and durable enough to withstand battlefield conditions. The cutting jaws had to be hardened steel to maintain their edge. The handles had to provide sufficient leverage without being so long they were awkward to carry or use. And they had to be reliable because a wire cutter that failed in no man's land could be a death sentence. Picks, axes, hammers, saws, all had to be field tested and optimized. The British even developed specialized tools like the trench spade, which combined a shovel with a pick point, and the billhook, used for cutting brush and stakes. Each tool was an engineered component in the construction system. And we can't forget the mining tools. The tunnelers needed specialized equipment that civilian miners would recognize but with military modifications. Hand drills for boring shot holes had to be quiet. Wooden mallets replaced metal hammers to reduce noise. Even the wheelbarrows used to remove spoil from tunnels were specially designed with solid wooden wheels that wouldn't squeak or clatter. The engineering of hand tools might seem trivial compared to trenches and tunnels, but efficient tools meant work could be done faster with less fatigue, which meant better fortifications and fewer exhausted men. In a war where every advantage mattered, Tool engineering was another piece of the puzzle. The railway engineering also included traffic management systems that would be recognizable to modern railroad operators. With thousands of trains moving supplies to different sectors, you needed centralized control to prevent collisions and ensure efficient routing. The British developed telegraph-based traffic control systems where each section of track was divided into blocks. A train couldn't enter a block until the previous train had cleared it. It was an early version of signal systems still used today, implemented under wartime conditions. And the locomotives themselves were engineered for warfare conditions. They needed to be powerful enough to haul heavy loads, but small enough to navigate rough track. They needed to be reliable because breakdowns could paralyze supply lines. They needed to be repairable with limited tools and spare parts. The British even developed armoured locomotives for use in forward areas, with steel plates protecting the crew from shrapnel and small arms fire. The narrow gauge railways I mentioned earlier were engineering marvels in their own right. The track could be laid rapidly by hand, pulled up and moved just as quickly. The curves could be much tighter than standard gauge track, allowing routes through terrain that would be impossible for regular trains. But the engineering challenge was keeping the lightweight track from shifting or sinking under load. The solution was careful grading, ballast where possible, and continuous maintenance. Engineer units assigned to railway maintenance would patrol the tracks, making repairs, adjusting sections that had shifted, reinforcing weak spots. And the loading and unloading systems were engineered for efficiency. Standardized cargo containers, essentially the ancestors of modern shipping containers, allowed rapid transfer between different types of transport. A container could be loaded onto a truck, moved to a standard gauge rail car, transferred to a narrow gauge car, then carried forward by horse cart or human porters, all without unpacking and repacking the contents. This modular system reduced loading time and handling damage. I want to close this section by talking about something that encapsulates everything we've discussed: the Hindenburg Line. When the Germans decided to consolidate their positions in early 1917, they didn't just dig new trenches, they engineered the most sophisticated defensive system the world had ever seen. The Hindenburg Line was a masterpiece of military engineering that incorporated every lesson learned from 2.5 years of warfare. The line wasn't a single trench. It was a defensive zone 10 miles deep in places. The forward zone had outposts and listening posts that would detect and delay attackers. Behind that, the main defensive zone with multiple trench lines, massive concrete bunkers, cleared fields of fire, elaborate wire obstacles, pre-sighted artillery positions, everything calculated to channel attackers into killing zones. And behind that, reserve lines where counter-attack forces could mass without being targeted by enemy artillery. The engineering sophistication was remarkable. The trenches were wider and deeper than earlier designs, with better revetments and drainage. The dugouts were deeper, many going down 30 or 40 feet with reinforced concrete roofs. The wire obstacles were broader and more complex, incorporating new patterns developed through experience. The concrete bunkers had overlapping fields of fire, calculated so that every approach was covered by multiple machine guns. Artillery positions were engineered, with overhead protection and multiple firing positions, so guns could be quickly moved if a position was targeted, and the whole system was built with reverse slope defense in mind. The main positions were on the rear slopes of ridges, invisible from enemy observation posts. Attackers would have to advance over the crest into a killing zone while under fire from positions they couldn't see until they were already committed. It was terrain engineering combined with fortification engineering to create a nearly impenetrable defense. The construction of the Hindenburg Line was a massive engineering project that involved hundreds of thousands of men over months of intensive work, but it was planned and executed with German efficiency. They had blueprints, specifications, material schedules, labor allocations, everything organized like a civilian construction project. They used the withdrawal to the Hindenburg Line to destroy everything behind them, implementing a scorched earth policy that eliminated any infrastructure the Allies could use, while simultaneously building the most advanced fortifications of the war. When the Allies finally broke through the Hindenburg Line in September and October 1918, it wasn't through superior engineering. It was through combined arms tactics using tanks, aircraft, artillery, and infantry in coordinated assaults that the Germans couldn't counter. But the fact that it took the full weight of Allied military power at its peak to break the Hindenburg Line is testament to how well it was engineered. All of this, everything I've described, was built and maintained by ordinary men under extraordinary circumstances. The engineering of the Western Front wasn't done by professional engineers in most cases. It was done by miners who became tunnelers, by railway workers who became track layers, by carpenters who became trench builders, by ordinary soldiers who learned engineering on the job because their lives depended on it. They didn't have computers or calculators. They had slide rules and field manuals and experience bought with blood. They worked under fire, in mud, in conditions that would shut down any modern construction site. And they built something that, for all its